Hey everybody, welcome to the stream. So few days back on off stream, I was trying to create a model which recognizes rock, paper and scissors from the images. I used this dataset, rock, paper and scissors dataset from Kaggle, and at that time I had not learned, new tricks. So I was getting this kind of results. So today we are going to implement new tricks that I learned, new tricks and the techniques that I learned from the FastAI course and implement in this project. By the way, you don't need to know how this game is played, rock, paper, scissors. It's a simple game, but for this model, for this purpose, you only have to know that this kind of hand position is for papers, and this kind of fist position is for rock, and this kind of position is for scissors. All right, so you just have to classify this images, different hand gestures, into rock, paper and scissors categories. So that's what we are concerned with right now. I don't need to know how this game is played or the rules which are involved in this game. All right, okay, then let's try to improve the model. We get the library. I have already uploaded the dataset inside the Google Drive. So right, I have gotten the path of the training. Yes, Asutosh, this is related to artificial intelligence. I'm trying to create a model. Yeah, I'm trying to create a model which can recognize this kind of different gestures of hand. So, do you know how this game is played, rock, paper or scissors? Yeah, so that's what I'm trying to create basically. So what I'm trying to create is a model, or I can say a software program which takes images of different gestures, like for rock, paper or scissors, and it will recognize it as such, if this is a rock or a paper or a scissors. So that's what I'm concerned with right now. I'm not going to build the game, the proper game. I'm just creating the model in this stream, and I have got pretty much accurate results. Like for most of the time, the model that I implemented is giving me accurate results, but in this stream I'm going to try to improve this model further, because it was still giving me some false negative and false positives. Yeah, sure, thanks. Right, we have the data block, get image files. This is considerable. We are using the random subset splitter, so we are not using the whole data set. I've forgotten what I have implemented, so I will be reviewing it. So I used the random subset splitter. Let me check how many images we have inside the dataset. All right, we have 2925 in total images. So, and I have used only 0.4% for the training set and 0.1% for the validation set. I guess I can use the whole data set because it's not that much. 2900, it's not that many images. Maybe I will replace it with the full data set afterwards. For now, let's skip this much. So let's get the data block as well. Now we can check the data sets using rps.datasets, I guess. Yes, I can pass the path variable. Right, let's check what is inside datasets now. Datasets dot train, and I guess it should be, what attributes do we have inside train? Let's just print the train and see what it contains. All right, so datasets.terrain contains 1000 images, and let's also check the validation dataset. Validation dataset contains 252 images, so that's enough for now. Let's get the data loader. By the way, for in this model, I'm just using this training folder. I'm not using the extra images inside test and validation set, although I can use those as well. I can get another splitter and get the images accordingly. But I guess this is enough for now. Maybe I will try to improve the data block later. Alright, so I have the data loaders now. Let's check the batch as well. Let me review what kind of transforms I'm applying. So this is alright. I'm just applying the batch transform. And I guess those images are already precisely, they are all 300 by 300 pixels. So I guess I don't need to resize them further or apply any transformations. Batch transform, we are doing augmentation transform. So this is the kind of augmentation we are doing: rotating, changing the brightness, saturation, and all that. Blurring, I don't think we are blurring. Yeah, let's roll with it. And in this time we are applying this different item transform, randomize resize crop. We are randomly resizing it to 224 and scaling it for 0.5. Let's get, by the way, I already have this model exported, I guess. Yes, I did export the model. Let me check. Where is it? RPS resonated in export, including data export and including data randomized research. So I have 3 model exported, and I guess this is the one that I optimized, most optimized one. This is the one which is most optimized, I guess. So I exported 3 different models. This could be the last one. Oops. Randomize resize. Let me check the FastAI book to see what kind of transformation we should apply. Right, we can apply this precising, but I think we don't need to precise it. Maybe we should. And for the record, while I was implementing this model, I didn't know about this precising technique. So I guess we should try to implement it and see what kind of results we get. So this is how we are precising it. First we are resizing the image, then after that we are applying the augmentation transform. And while we are applying the transform, we are also resizing it again to 224. Minimize data destruction and maintaining good performance. Let's try to import the model that we optimized and see what kind of results it is giving us. Then we'll try to optimize it further using the new techniques. So I can get the learner using this export. Let me check which model I want to import. So this I have named as ink data export. Ink data, I guess, means I have forgotten why I gave this name. Ink data, I mean, I think I gave that name because of increasing the data. I might have increased the data size, I think. And export. Why would I give export as the name? And increase data plus randomize resize crop. Alright, so let's get this randomized resize cropped version. You already have gotten it. You already written the code for the import. Let's get that one now. Wait, this is for the increased data only. Have we imported another one? I think we didn't. Let's get that one then. We want this model. Let's copy the path. Let's get the learner. I should call this learner something else. Let's call it let's call it learn one. Cool, we have imported the model. Now let's try to use Let me see how can we display the losses. Do I have this image already? It is inside F. I might not have the image here. I have deleted this variable F which contained the path. Let me check if I have the image or not. RPS my datasets. Yeah, I have the images. Let me try to predict this paper one. Copy the path and I should place it inside a variable F. Let me replace this with F. Okay, I should change this to learn F, learn one. Cool, it is predicting as paper. Let's check the image as well. Alright, this image has been classified correctly. Let's get paper 2. Paper 2 is correctly classified as well. That's good. What about paper 3? What about scissors 1? Scissors. Let's get scissors 2. Cool, it has been classified correctly as well. Let me try to plot the confusion matrix. Alright, I created a loop to predict all the images inside this folder, so I can use this. I might have to change this thing. Should we learn one? So this one has been classified incorrectly. Rock 1 has been classified as a scissors. This rock as paper. This rock as rock. Rock as rock. Paper, paper, paper. Scissors, scissors. So it seems that our model is incorrectly classifying the rocks. So that's what we are going to that's what we are going to try to improve. I think we should try to get this kind of matrix as well, confusion matrix. Let me plot a confusion matrix for learn one. Can't we plot the confusion matrix using the imported model? Why is that giving us error? Your generator is empty. If I try to plot it over here, it is still giving us error. So I guess we can't use the imported model to display the confusion matrix. We might have to retrain the model, I guess. Let me try to retrain it from scratch. I should first try to use the randomized resize crop, I guess. Alright, let's get the randomized resize crop version. And get the learner. It's going to take time because we have almost 1000 images. Should I try to decrease the dataset and then use these techniques? Yeah, I think I should try to decrease the dataset size and then try to train the model. That way it will be much faster to experiment different techniques. We should decrease the random subsets with the training size to, yes, 0.1% or something. 0.1% gives us 252 images. We can get I think around 500 images. What if we were to use only 500? Well, 200 images not that much worse. We can use 200 images to experiment with the model, I guess. Afterward we will increase it. So I guess I will keep this as 0.2 or something. That will give us 500 images for training, and this should be, I guess, 50 or something. So we are getting down up to 0.04% error rate. And now if we try to plot the confusion matrix, I should change this from learn to learn 1 to learn. Alright, so it seems 7 of the scissors are classified as paper, and 4 of the papers are classified as scissors. So our model is confusing scissors and papers most of the time, and almost all of the rocks, not almost all of the rocks are classified correctly. 86%, 86 images, all of them are classified correctly. Alright, and let's check the top losses. Let me delete this. So these are the top losses. Let me delete this row as well. I don't need to check the previous results so that I don't get confused. Right, so this is classified as a scissor, So what could be happening? Scissors, scissors. But now this is classified as a paper. Why is that the case? And this paper has been classified as a rock. This paper as a rock. Yeah, one of them is classified as a rock. So I guess, and this scissor is being classified as a paper. I think I should also add one more class for the gestures which are neither, which doesn't belong to rock, paper or scissors. So it should be something as none or something. So if I were to do this, it should be none, because it's neither a rock nor a paper, also not scissors. I think that way we'll see later on. Let's try to roll with this model. Alright, these are the results we are getting out of the randomized resize crop. Let me try to reduce the data set size and see if we can still get this kind of results. Let's get 0.2%, I think, and 0.05%. Cool. This many will suffice for now. Let's copy this learner and try to train it and compare the results with the less data. It is definitely training faster, but the error rate has been increased. The error rate is not that much bad. In fact, the validation loss, we are getting almost the same kind of results. So I think we should try to train it on the decreased data, because we are also getting increased speed as well. Let me try to plot the matrix as well. At this time we are almost getting all the papers and rock correctly classified. Only the Caesars has been classified as incorrectly this time. Good. So it seems that decreasing the data set size increase the efficiency. And if we check the top losses, these are the top losses. Let me export this model as, I should name it, let's keep it as randomized resize crop only. I should call it less data. Let's remove export 1.1. Right, I have imported that model now. Let me clean this up a bit. Let's delete these results. Now let's try to improve it. We have used the randomized resize crop technique. Now let's try to use precising, I guess. So this is how we can do precising. We precise it to 460 first. But in our case we have all the images as 300 by 300. So I guess we will have to keep this lower and this thing much lower, but that will lose most of the data. Let's try to implement it anyway. We can apply the new transform. Let's copy this transform. During the precising optimization, we might have to tune this parameter as well, minimum scale. So we can keep this. So as we have 300 by 300 images, we can resize it to something like 224. Let's give 224 as the resizing step, and can keep this as, I guess, 200 or something. That might be all right. Mhm. this data loader. Let me just write a comment. This is precising step. Precising. Can I copy this cell down? How do I copy it down? Keyboard shortcuts. Where are the shortcuts? Control image. I want to copy the cell downwards. Copy cell or selection. The shortcut has not been selected. Let's not set it right now. Let's copy this cell downwards. Copy cell. I cutted it. Control MZ. Did we get it back? What the hell? I lost the results. That's what I'm doing, man. Control MZ. Still I'm not getting the cell back. That's alright. Let me just thank God I got it back. Or we would have lost the results. We would have nothing to compare it with. So what I want to do is copy this cell, paste it. Okay, we have got two models now. Let me copy this comment, write it over here. So this is for the precising step. Now let's try to train it. Check the results for the precising, data transformation and augmentation. Oh, it seems our model is improving. We got up to 0.01%. That's not bad. 0.02. Oh, in fact, the model has improved a bit using the precising step. Let's try to plot the confusion matrix for the precising step. Copy the cell, paste it. This should be the precising step. Oops, I don't want it twice. Let me delete the third one. Let me copy the command precising. This is for the precising step. And let's plot the confusion matrix for the precising step. Awesome, we are getting down up to 3 false negatives. False negatives or positives? False positives, I should say. So previously we were getting 6 and we are down to 3 only. So that's an improvement. Let's try to use that model to predict the images that I have downloaded inside this folder, which are this kind of images which I generated myself. Rock, paper as paper. Good. So it seems that just using the precising step, our model has improved drastically. We are not even done with all the techniques that we can implement. I've just used the data augmentation and we are down to almost 0.002. That this 99% accuracy, I think. That's awesome. Almost 99% accuracy. Let's see what other techniques we have inside our bag. Cross and okay, this is not a technique that we need. Model interpretation improvement, yeah. So these are the techniques that we can use. We can use the learning rate finder, can use unfreezing and manual unfreezing and using this technique, and then can use discriminative learning rate as well. So let's try to use that. First we will check for the learning rate. We need to find a proper learning rate. First of all, let's export this model. We're getting awesome results, so let's call it less data randomized resize. This is not randomized resize, it is resized. Precising, okay, and 1.1 is all right. Okay, we have exported the model now. Now let's try to use learning rate finder. Meanwhile, let's also plot the top losses. So all of these are classified correctly. We only have 3 images which are not classified correctly, so we should change this to 3 only. So these 3 images were classified incorrectly. Alright, I can this might be because the gap between these 2 fingers is wider, so that's why it may be classifying it as a paper, I guess. Alright, we will try to improve it further. Let's get the learning rate first of all. So this will give us the learning rate that we can use. By default it is using, I guess, 0.2 or something. It might be using 0.2 as the base learning rate. Let's check the base learning rate. Show me the learning rate, man. It will show us afterwards, I guess, while it is loading the model. It won't show us the pop-up. All right, we have the learning rate now. Let's see which learning rate we can use. So at this slope, the loss is decreasing. So we should use a learning rate between this range. And I always have to refer this image because I don't know how to convert this R in a log. This graph is in a logarithmic scale. So we have to convert this back to, I don't know what it is called. So we have to convert this logarithmic scale and use that base learning rate. So for this image, for this graph, they have used 3 raised to minus 3. So this 1 e raised to minus 3 maps to 3 raised to minus 3. I think we can use the same learning rate. So let's use 3 raised to minus 3 as well. So now we use 3 raised to minus 3. Let's call this single LR find. Now let's check the results. We're just fine-tuning now 8 for 2 epochs. Let's increase it to 8 epochs. Previously we were using 8 epochs, so we should train this thing for 8 epochs as well. Point 1. Wait, it seems that it has started to get worse after the second epoch. So after using the base learning rate, it seems that it got worse. Excuse me. Previously we were down to 0.02%, 0.02 law error rate, and it was not getting worse. But now that we are using a custom, or I should say a different learning rate, it seems our model has not improved. In fact, it has got a lot worse. So let's see what's the problem. If we check the fine-tuning method, the default base learning rate is 0.002. Let's see, 0.3 raised to minus 3 is 0.003, right? 3 raised to minus 3 means 0.00. Yeah, it is 0.003. So it seems increasing the learning rate didn't improve our model. So our learning rate was this much, and we give it this much. So what if I try to change this to no, I don't think so. It should be 3 only, but there should be 2, which was enough for the results we were getting, right? 2 raised to minus 3 is 1002, which is already the default learning rate. So yes, we shouldn't have increased the learning rate because it started to it got worse. Alright, it seems 2 raised to minus 3 is the sweet spot, although it did decrease, it increased a bit on the last epoch. So we'll keep this default learning rate for now. So let's try to use this different technique, which is unfreezing and transfer learning. So for this technique, we will first train it for one cycle using the learning rate that we found out, which was 2 raised to minus 3. So we are just fitting for one cycle. So this will only train the randomly added layers. This won't train the pre-trained layers. This is basically doing this step, but by default it is just when we call the fine-tune method, it just does this epoch cycle one time. So this time we are doing it for 3 cycles. So we are down to 0.45, 0.35. So we have improved. Now let's unfreeze the layers, all the layers. So this will unfreeze all the pre-trained layers as well. And now we can use the LR find method to find the learning rate, which will be adequate for all the layers, not just for the pre-trained or randomly added layers. As this model is already trained, therefore we'll get this kind of graph, almost flat graph, and it starts to get worse as we increase the learning rate. So we should select something from this range. Let's see what kind of graph we get. Oh damn, this is an ugly graph. We are not getting a flat graph, so it seems right, the loss has been decreasing, seems. So we should choose a learning rate from this range, right? One e raised to minus 5. Let's see what we should select. Let's use 10 e raised to minus 5 as well in this model. So now we are going to train the last cycle, which will train all the layers, and we will do it for 6 epochs this time. And we will use 1 e raised to minus 5 in this case as well. Well, okay, is it not improving at all or what? I think we should train it for 8 epochs. So using this learning rate, it seems our model didn't train that much. Previously we're getting this kind of results. I think I should increase the learning rate. So let's do that. Get the model again and fit it for 1 cycle. This time we will fit it for 8 epochs and use a different learning rate. We will use, let's see, we will use 1 raised to minus 4 this time. Alright, let's use 1 raised to minus 4 this time and train it. Down to 0.17, 0.13, 0.17 again. Oops, it has started to increase. So validation loss is increasing, it seems. Or is it? Just going like this. So that didn't improve our model that much. So these are the results of the custom learning rate. We should try to use the discriminative learning rates this time, I think. So let's use the discriminative learning rate and check the results. We will pass 3 raised to minus 3. That's what we used, right? Now we used 2 raised to minus 3. So we will use 2 raised to minus 3 over here. And this here we will use, let's just use this range. Point 0.28, 0.6, 0.26. Nope, it seems even after using the discriminative learning rates, our model has not improved. And it was giving us adequate results just using the custom LR find. Custom, I mean different, or the default LR find. So this techniques didn't improve our model that much. So this time let's try to use some more data and see what kind of results we get. This time let's use should we use 0.4 that we were previously using? Sure, let's just use 0.4 and 0.1, right? And we are going to use the precising. Let's copy this cell. This should be called precising and increase the data. All right, let's fine tune it now. While we are at it, let's pass the base learning rate as well. We were using 2 e raised to minus 3, right? So let's use 2 e raised to minus 3 here as well. Let's check the results. It's going to take a while. Oh, it is not. Maybe it is because of the learning rate. No, that can't be the reason. But it seems that it has speed up, something has speed up the training part. Oops, it seems after increasing the data, our model got somewhat worse. It is starting to fluctuate. Wait, we are down to 0.7%, 0.07 error rate. But the validation loss has gotten up to 0.15 only. What if we train it further? Let's train it for valley points, not 812. 0.03. Okay, we are getting good results, it seems. Alright, we have plateaued at 0.03, I guess, for from 7th epoch. So 7 epochs are sufficient, I guess. While we are at it, let's export the model. This we should call as precising, but increase the detail. How much have we increased? Okay, let's not mention it. Let's try to plot the graph, the confusion matrix for precising and increased data. Copy cell, cut, copy, precising and increase the data. Okay, since papers are getting confused with rocks, and rocks are getting, scissors are getting confused at rocks as well, and scissors are getting confused as paper as well. Let's check the top losses. So these are the images which were getting confused. Paper, rock, paper. Let's check the predictions on this, our custom images. Rock, 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 paper, 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 paper. Alright, so most of them are classified correctly. You can also check this dataset that we have not touched yet. Right, let's use this folder, validation. Copy the path, the validation. Let's check the results now. Paper, 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 rock, rock, scissor, scissor, rock, 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 paper, paper, rock, 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 rock. This one has been classified incorrectly. Let's check what it is. It is inside validation. Scissors higher one, right? Scissors higher one. This one. This one has been classified incorrectly. This is classified as a rock. Paper, paper, rock, rock, scissor, scissor, paper, paper, scissor 9 again is rock. Scissor 9. Okay, I have an idea why this is happening. Is our model biased or what? Because scissor 9 and scissor higher one are both from, both are dark images. So it seems our model is biased. This data set is not that much accurate, I guess. It should contain more this kind of images, which should not bias this. So let's check for the scissor 6, scissor, paper, scissor 8. So yeah, this one is also black. Rock, scissor 7. Again this one. Rock, paper, scissor, paper, rock. Wait, paper 1, rock. That's paper 1. This one. Scissor 1, scissor, paper, scissor, rock, scissor, rock. Okay. What kind of images do we have in the test set, the training set? Let's check it. Why does it contain only fair screen images? Wait, there are more images. I should check it out first. I have it on my local system as well. Let me check. This takes a lot of time to load. Here it is. So if I check the scissors, well, the folder contains all kinds of images. It should not be biased as this. It contains fair images as well as dark images as well. The data set contains all kind of images, so maybe I am incorrect in my supposition. Maybe it is not biased, but is it the data augmentation step? Because it might have applied brightness, or but it applies it randomly, so that might not cause trouble. Anywho, our model is pretty much accurate. We are getting down to 0.03%, so which is great. Let's check other notebooks and see what kind of results they are getting. Is it taking time? We have it 98% accuracy. This is top, right? Multi-class classification. Let's see what kind of results this guy is getting. Alright, I think we should increase the dataset size as well. is getting 0.98. Let's check the accuracy metrics as well. Accuracy. Point 0.91. Okay. It seems we have plateaued at 0.90. Oh, what the hell? This this results are very much different from this results. We have just changed the matrix only. We have not changed anything else. Why is that happening? The matrix should not, affect the model. This was just for us, right? The loss function is different, which is same for both of these models. Yet we are getting very much different results. What if I try to change it back to error rate? Because I will be back in 2 minutes. It seems after sixth epoch our model started, but only after third epoch we were getting down to this result, and after third epoch it started to get worse, so maybe it was overfitting it. Well, I'm guessing what if we try to use this techniques on all the data? I mean the custom LR find and all that. Let's try to use those techniques and see if we can get better results this time. Those, okay, they are over here. So let's try to find the LR learning rate. I won't be surprised if it gives us different results this time, because we are using a whole lot of data this time. It is almost like this graph. So I guess 2 e raised to minus 3 is not bad. So it's alright for this. Now let's try to use the custom method. While we are at it, let's use this to train it for 8 epochs. Well, we already used it, so we need not do it. Alright, we are getting almost the same results, but it seems the validation lot started to get worse after fourth epoch. So we might be overfitting the model. Let's try to use the custom method. Point to 4. So this is just for the randomly added layer. We are down to 0.16. Let's unfreeze the pre-trained layers and find the learning rate. All right, this time we are getting this. First, the loss started to decrease over here. Then it got almost bumpy for this range, and it got almost flat for this range. So I think we should select something from this range. Let's select what should we select? Let's select 1 raised to minus 5. 4 was alright as well, I guess. Alright, let's fit the last cycle using 1 raised to minus 4. This will train all the layers, including the pre-trained ones. We are down to 0.15 on the first epoch. 0.07. 0.04. All right. Oh, it started to overshoot, I guess. Oops, our model has started to overfit. Oh no, wait, it has started to decrease again. Alright, this time we got down up to 0.07. Not bad. Let's try to check for the discriminative learning rate. I should have saved this model. It was giving us 0.07, which is different from this. So it did improve a bit. Let's check the discriminative learning rates. We will save this one if it is an optimized version. It seems using the discriminative learning rate, we are down to 0.02. It's pretty accurate model, I should say. And also we'll try to use different metrics which is accuracy rate, and check what kind of accuracy we are getting. It seems we have flattened, so we should have just used, I guess, 6 epochs. That would have suffice. Let's get this model. This time we will select accuracy rate. And we will only train it for, let's see, 7 epochs. Yeah, 7 epochs. Let's use 7 epochs. Why does this happen? Whenever I try to use the accuracy, this validation loss also changes. It got worse. So let me try to change this back to error rate. Why does this happen? Previously we were getting this kind of results for the exact same model. We have only changed the epochs this time. We're getting up to 0.2 only. So let me try to change this to 12 only. Right. I think I know what might be happening. Because we are using a discriminative learning rate, it changes, it selects. No, wait, that won't be, that can't be the reason. Why do we have this kind of uncertainty? Sometimes our model overfits and sometimes it doesn't. For the same hyperparameters, it is overfitting very badly this time. Like the validation loss is almost 0.41 and we are getting almost down to 0.11 towards the like cycles. Why is this happening? Why do we have this kind of uncertainty? Is it because of the discriminative learning rate? We are using a ResNet 34. Previously we are using, let me check. It was ResNet 18. Okay. We have even changed the model. So this was ResNet 18 and we are using ResNet 54 this in this. So let me change this. That might be the reason we are getting different results. So let's check if I use a ResNet 18 over here. Let's use ResNet 18 and try to find the learning rate. Alright, so this learning rate seems okay. So now let's call this ResNet 18. Let me compare the results now. It should definitely give us different results. It started to overfit again. If we use resonate 18 over here as well, right? And the learning rate was same. And here also we are using resonate 18. We got up to 0.04 on second epoch. So we should fine tune it for just 2 epochs. And let's try to use custom methods. First of all, let me try to change this to 3 epochs and check the results. Okay, this is not bad, but getting 0.08. Let's copy the steps and we will use resonate 18 this time. Let's unfreeze the pre-trained layer and find the learning rate. Yeah, so we can use this point as, so let's use that point. Oh wait, it did improve our model. We're getting up to 0.01. Oh, that's nice. I'm definitely going to save this model. But it started to overfit after 4 epochs. Let me change this to 4 epochs. So I should get this first. then this, and this, and this should be only for 8 epochs this time. Sorry, 4 epochs. The hell, we are getting a different graph this time. And this is a lot worse. Alright, we are getting down to 0.01. I'm gonna save this model. It is increased data precising, and also it is custom LR. Okay, now we have saved it. Let's plot. What should I plot? I want to plot the confusion matrix. Custom LR. Awesome. Not that bad. Now that I have saved it, let me try to use this for resonant 18 for discriminative learning rates as well. One, three, one. Right, it seems after using the discriminative learning rates, our model is not improving that much. But I'm satisfied with this result. No, this is definitely not the result that I want. I'm satisfied with 0.01. So I'm gonna use this. Okay. We can create a new cell. Let me delete the slice. So this time I'm going to display the accuracy. So yeah, these are definitely not the results that I want. So it seems the custom unfreezing and freezing works perfectly. Okay, it says we are only achieving 0.87 accuracy. I want to achieve up to 0.98, 99% accuracy like this guys have. So it seems we are still a long way to go. I might have to change different things and optimize it further. But I guess this is it for this stream. I'm not gonna try to optimize it further. Maybe I will do it in the future and stream it again. Or maybe I won't. Let's see. So alright then guys, I will see you again in the next stream. This is it. Goodbye.